Hi everyone, let's now factor our polynomial over C, the set of complex numbers, and find all of its complex zeros. That's a typo there. So we've already factored this polynomial over R, the set of real numbers. Which of these factors can now break down over C? X is good. These two other linear factors are also good. It's this prime or irreducible quadratic over the reals that we can break down further. X squared plus 3. How can we factor it over C? Well, look at it this way. What if we had to factor x squared minus 3? If we had to factor x squared minus 3, we could factor that as a difference of two squares. Maybe not nice squares, but squares. We would factor x squared minus 3 as x plus what? And x minus what? 3 is the square of what number? The square root of 3. But now wait a minute. We want to factor x squared plus 3, not x squared minus 3, which means we have to insert what? Much like a scientist, we have to insert the i's. I over here, or you can move it in front of the radical. That might be safer. I over here, or move it in front here. So how can we factor x squared plus 3? It now breaks down over C as a product of these two linear factors, x plus I root 3 and x minus I root 3. So now, notice that when we factor this fifth degree polynomial over C, we're now factoring it as a product of 5 linear factors. And that's not a coincidence. Also, what are the 5 complex zeros? Well, we already got the 3 real zeros from earlier when we factored over R. Because x was a factor, 0 was a 0. Because x plus root 2 is a factor, negative root 2 is a 0. And because x minus root 2 is a factor, positive root 2 is a 0. But now, since x plus I root 3 is a factor over C, negative I root 3 is a 0. And because x minus I root 3 is a factor, I root 3 is a complex 0. So these are the 5 complex zeros. Okay, and the fact that our list of complex zeros looks like this, it's not a coincidence. There are several patterns that do extend to theorems. We'll talk about those theorems next time.